Yeah, there I am.
All right, welcome back, everyone. Hope you enjoyed your lunch. So Bram is going to now finish his lecture with this last lecture. Bram?
Thank you. Yes. Yes, in this lecture I will sketch using all of Peter's input how we can compute the K-theory of C star reduced of G for a real semi-simple Lie group. And this procedure will consist of first finding a decomposition of C star reduced of G as one of these C0 direct sums that I discussed in my previous lecture, and then find a similar but Morita equivalent description which allows us to compute the K-theory. So I didn't get to my main statement of last lecture, which is, as I just said, going to be input, and that is the following, namely that if A and B are Morita equivalent, then their K-theories are isomorphic. So that's one of the main reasons for considering Morita equivalence, as we saw in some examples. Algebras that look quite dissimilar can be actually Morita equivalent, and this allows you to, when you are interested in a K-theory computation, to replace your algebra by something more tractable that you understand to compute the K-theory. I will just say very briefly something about the proof in view of time. So if we have an equivalence bimodule with dual E star, then as I said, without introducing tensor products, we have these properties. So if you look at this with all the B's and A's, and then you can think of a Morita equivalence bimodule as somehow a square root of your algebra as a module, such that if you multiply them using the tensor product in one way, you get A, and if you multiply them using the tensor product in another way, you get B. And now let x0, x1, f be an element in K0 of A in this Kasparov picture. So this is one of the reasons why this picture has advantages for at least theoretical purposes. And because we're working with non-unital algebra. So in the unital case, you can show that Morita equivalence bimodule is always projective from both sides, and then in the projective module picture of K-theory, you will get your isomorphism by just tensoring. In the non-unital setting, this is much less obvious why this would carry over, but in the Kasparov picture, the exact same idea carries over. Then, so we're going to define the map induced by the Morita equivalence is defined as, well, you take this Kasparov element and you map it to just the tensor products. And again, this looks all fairly algebraic. Of course, there is analysis involved in defining all these things. And this map is an isomorphism with inverse given by, so this is an isomorphism with inverse given by, well, the map defined in the same way, but then using this dual module. And the properties that I listed here make sure that if you compose these maps, you actually tensoring with either A or B from the right and tensoring a module by the algebra over the algebra is the identity map. So that's a neat way to think of Morita equivalence. And yeah, so this means that if we can compute the K-theory of a Morita equivalent algebra, we get the K-theory of the algebra we are interested in. All right, so now let's have a look at this K-theory of C star G. Let's see what I shall and shall not say. So calculation, or not, wait, I will say a description of C star reduced G. Well, first, from Peter's lectures, we find that the tempered dual of G admits the following disjoint union description. Which I will clarify in due course. So here, sigma in M hat and G hat P sigma is a set of irreps contained in what Peter called this representation over here. So we saw that in some sense all representations of A, all induced representations by sigma and something on A occur here. And so that's what G hat P sigma means. And now what is this disjoint union indexed by? Well, P sigma is an equivalence class where a pair of a parabolic subgroup and a sigma on M hat is equivalent to a P prime, sigma on M hat, if for the decomposition P is LP times NP, there exists a K in the maximal compact such that up K of LP is LP prime and up K star of sigma is sigma prime. So we say that two such pairs are equivalent if they are conjugate by some element in a compact subgroup. So this gives us a description of the tempered dual in terms of these induced representations. Now we consider the space Z0 of A star P compact operators on int GP H sigma, where H sigma is the representation space that Peter showed all these representations are carried on. Then this group W sigma acts on this space, and we can define maps pi sigma, well, a priori from CC of G into this space, GP H sigma, and now we take the invariance with respect to the group W sigma. By setting pi sigma of F, so F is in CC of G, evaluated on a xi, so xi is in the dual of the Lie algebra of A, where we then said that this is the induced GP sigma nu xi tensor 1, and then acting on F, and as a notation I want to write pi sigma xi for this representation. So pi sigma xi of F. And then there's a proposition which I think is originally due to Wassermann, but the map pi sigma well, let me not write that here, extends to a star homomorphism, which I will also denote by pi sigma on C star reduced of G into this algebra of invariance, where the algebra structure comes from the fact that this is a space of functions with values in a C-star algebra, so we can pointwise multiply these elements. So this is a star homomorphism of C-star algebras. That's how you can view this. And then there is a theorem, which is, I think, certainly due to Wassermann, but some of the experts in the audience may correct me if I'm wrong. That the following map now we get the same direct sum over these equivalence classes of pairs P sigma, where we're now going to put here AP, oops, K induced representation GPH sigma, W sigma invariance, which, well, you can guess what this map does. It takes an F and it just puts it to pi sigma F, where you run over the whole index set. This is an isomorphism of C-star algebra. So, and here, of course, the right-hand side is one of these C0 direct sums. So we've decomposed C-star reduced of G into smaller bits associated to these parabolically induced representations. I forgot to mention that this star homomorphism in the proposition is actually surjective. So that's part of this result here. Surjective. So that means that the second map here in this theorem is also surjective. Injectivity follows from the description of the temper dual. So you can show that the kernel of this map would correspond to something that doesn't occur in any P sigma, which cannot happen unless it's zero.
There is a question: why does the map in the proposition extend to reduced C-star algebra?
Well, I must admit that I'm not expert enough to actually. So you have to prove a norm estimate. So the map in the proposition. Wait, let's see if we can.
Maybe a comment there is that
maybe Peter knows this. Knows some more.
The normal C-star G is the normal left convolution on L2 of G as a bound operator. And because the Plancherel transform is G equivariant, on the right-hand side, it corresponds to the operator norm of pi sigma psi of F. And so that correspondence comes from equivariance of the Poincaré transform, the Fourier transform. And then the norm going to 0 at infinity. Not immediately sure, but I think that should be okay.
Well, I think we don't doubt this is true. And of course, the question that was asked is crucial. I mean, that's what needs to be proved. That's a non-trivial statement.
Yeah.
That's exactly what needs work in this kind of proposition.
I mean, is this one of those things that Wasserman just said this is true and then didn't prove, and then Nigel, Pierre, and Tyrone proved, or is this proven in that short paper?
Wasserman didn't prove anything. This is basically this was worked out by Nigel, Pierre, and Tyrone.
Yeah, that's where I took it from too. So maybe I can mention that actually. So that's actually, as far as I understand, the history of this was that Wasserman announced several important results in this area, the details of which are still being filled in. But I don't think anyone doubts the validity of the statements, as it often happens in mathematical research. We'll try to make also a comprehensive reference list for this argument, for the setup of this whole proof. Okay, so this means we've decomposed the reduced C-star algebra. And now this is not enough to compute the K-theory, because now we want to replace this right-hand side, so the infinite direct sum here, we want to replace it by Morita equivalent direct sum. So actually what we will do is we will find Morita equivalent algebras to each of the components in this direct sum. And that will eventually allow us to compute the K-theory. So going ahead with that, consider the following. So A star P times the representation space. Yes. And we view this as a field of Hilbert spaces over, well, the vector space A star P. But we view this vector space now just as a trivial manifold, a locally compact space. So viewed as a locally compact space. Then W sigma acts on this field via alpha W.
There's a question about the A star P notation.
I don't know what the question is, but I think Peter wrote this as HOM A P R. I don't know if this clears it up. So this is just the vector space dual of AP, and that's a vector space itself. Is that clearing it up?
Sure. I'll put a link to lectures, slides of Peter, just in case it comes in handy.
So here.
T is the Lie algebra of the A component of P in the long-length decomposition. Is that right, Peter? Yeah. That's the AP.
Yes, and so I'm indexing it by, I don't remember, did you also index it by P? I mean, usually you fix a decomposition, then you just work with A, but in this setting, we're varying the parabolics, so that's why the P is sometimes kept track of. Yeah, and U W phi is the representation of W sigma. On this space. So therefore, C0 of A star with values in the induced representation space is the same as the space of sections of this trivial bundle. So if I would use section notation gamma, then it would look like this. But this is a rather trivial identification. This carries a W sigma action as well. Now we can define another action by alpha naught of W acting on phi V, V phi, and then we just take the representation associated to the zero element, which acts on the same space still. So maybe I should have said here, maybe it's better to think of the following sigma, and then I think mu phi we use 1. But since these all act on the same space, we can think of them as acting on the same space. And then the following proposition, and this is sort of where the essential ingredient is, namely that the actions of alpha and alpha naught of W sigma on C0 of A star is GPH sigma, they are unitarily equivalent. So this means that there is a unitary that conjugates these two actions. And, well, the proof relies on the fact that 0 in AP star can be viewed as an alpha equivariant deformation retract. And from that, it follows that the two equivariant bundles must be isomorphic. So this is where some homotopy theory comes into the game. Hence the two equivariant bundles are isomorphic. I wasn't really able to find an explicit expression for this retraction, but it must, I guess, be known to some people. But you can sort of see how it should go. Okay, and from this, we derive following corollary, namely that the fixed point algebras C0 AP star I'm going to need to label them, otherwise there's no. So I'll write alpha of W sigma and the second fixed point algebra alpha naught. They are isomorphic. That just follows directly from this unitary equivalence. If an element is invariant for the one group action, it is invariant for the other. And we will have a preference for, we will work with C0 A star. Well, let me make my life easier. We will work with this one. So now we're going to work with the second action that Peter described. So we recall R sigma inside W sigma. So there are different ways to think of this. You can define R sigma either like this or directly as a subgroup. If you define it in this way, then you can show that there is a splitting of the quotient map. You just choose one. And since it's a subgroup, this also acts on our field of Hilbert spaces, or well, let's just say on the representation space. This gives us an action, as Peter described, on the space of compact operators from the representation space into the little L2 of this finite group, where of course carries the left regular representation. Now let me state this as follows. You can look at the following bimodule. Of invariance. And so we see that we have here a space of functions on some, well, quotient vector space, but we view it just as a topological space with values in the compact operators from one Hilbert space to another. Okay, and then there is also these invariants. But the idea is that the compact operators from one space to another, of course, carries two actions, one from the left and one from the right, by compact operators on either Hilbert space. So the compact operators on this space, they act on this set of compact operators from the left and here from the right. And so you can view this as a bimodule. And so this is a bimodule for C0 PW sigma compacts. And then invariance. And this is a Morita equivalence. And from that, so this is this doesn't work in full generality. You need some conditions on the actions and the groups, but because these are all finite groups, and the algebras and modules are constructed from actual Hilbert spaces and functions into those. This is this is a reasonable result, I would say. And from that, so together with our description of C star G that we already had, we find that there is a Morita equivalence of C star algebras between C star reduced of G and the sum over equivalence classes of parabolics with C0 A star W sigma is that right? No, sigma K L2 of R sigma and then the invariance. So this follows by combining the Morita equivalence.
Maybe you want to have a sigma, W sigma prime there that you quotient A star.
Yeah, wait a second. Where?
A star modulo W sigma prime on the right hand side.
Here.
Yeah.
Yeah.
Part of W sigma acts trivially on the compact operators.
Yeah. And then this is what we want to have, right? Yes. Okay, and now to compute the K-theory, of C star G, it suffices to compute the K-theory of the components here. And then use the direct sum result. So that now follows from, of course, we need to make distinctions, as Peter was also already hinting at. So if W sigma is not equal to the identity element, then it turns out that C0 AP star W sigma prime is R sigma 0 equivariantly contractible and hence the K-theory of the fixed point algebra is 0. So that means that we can discard in direct sum the components for which, then I need to put the prime here again, for which W sigma prime is not trivial. So we can discard those, and then that means that the computation is now reliant on the case where W sigma is the identity. Then we need to make two case distinctions, which we find that the dimension of G mod K comes in, and
You want primes on those W omegas.
oh my God.
W.
W's.
Yeah.
Yes. Yeah, I keep forgetting that. Thanks. So in the degree of the K-theory that's given by the dimension of G mod K, there is exactly one generator, so this group is free abelian on that single generator, and in the other degree, the group is trivial. Hence, we find that for a reductive real B group, the K-theory, wait, let me write this properly. Is a direct sum of just z's over equivalence classes of p sigma such that w prime sigma is the identity and the group is free abelian for those representations. So the K-theory of the real reductive group picks up a generator for each of these representations sigma and nothing else. So in the other degree, the group is 0. Well, that went a little faster than I thought. Yeah, I could stop here. I could say a little bit about some of the Morita equivalences, some of the general results, or yeah, that these Morita equivalences came about. But maybe it's a good point to stop actually.
Let's stop here and then we can have questions. Thank you, Rob.
Or comments from the experts in the audience.
So in the SL2R case, you know that the discrete series will give, each one will give a Z copy, right? There was some subtlety, right? You get 0 from one of the principal series family, but non-trivial contribution from the other one. Can anyone remind us that story?
I can. Just wants to comment. Yes, so the W sigma prime was trivial for the non-spherical principal series of SL2R. Was Z mod 2 for the spherical principal series. And therefore, in the case of SL2R, you get one generator for every discrete series representation and one for the whole non-spherical principal series. And the spherical principal series gives nothing. And from the K-theory point of view, it makes sense because the spherical principal series is a half-line, closed half-line, and also the topological K-theory of a closed half-line is 0. So you expect that to be 0.
I mean, I often hear about this subtlety with this limit of discrete series making a difference and K-theory is detecting all that. Is that, would anyone want to say a few words about that? Maybe Roger could tell us about that. Maybe it's a good place to mention this.
So it's quite true that the limit of discrete series, that pair of representations does contribute one generator to the K-theory. to K0, I should say. There's another feature of the limit of discrete series, I believe, which has to do with their characters, which are not identical to the characters of the discrete series, but somehow very closely related to them. So I think there's a link. There's another reason why they call limit of discrete series, because of their Harish-Chandra characters. Yeah.
I see. So when you look at the characters, they look like they're in the limit of the characters of the discrete series, or like parameter 0 or something like that.
Something like that, yes. Certainly the Kohn-Kasparov conjecture for SL2R would not be true unless the limit of discrete series for SL2R contributed one generation. Yes.
But it sounds like from here that they do not, it's not them they're contributing, this the whole family, they sit at the top of this non-spherical family. And I guess maybe their existence, so I guess if at the tip of the non-spherical family at parameter 0, if it wasn't reducible, it would be like the other one, they would contribute nothing, I guess, right?
Exactly.
That's because the reducibility there makes them contribute.
Yeah, it's this non-Hausdorff behavior at the tip of the non-spherical principal series, which is responsible for this phenomenon, if you like. Yes.
I see. So
Yes.
logically protected in that sense.
Yeah.
But it sounds like, I mean, we went through this whole very intricate machinery of this classification of this tempered representations, that big theory, and then we kind of tried to mimic that in a C-star way to get this description. So it looks like this description of the C-star reduced G is very representation theoretic knowledge, basically, right? It's and it seems to me that one of the main selling points of these reduced group C-star algebra is that you give some independent way into these representation theory of groups, but it looks like we use representation theory of G to describe this guy, and I feel like should go the other way around. You should maybe it's.
I think what you say is absolutely correct, and there's really heavy theorems from representation theory going into this description.
Mm-hmm.
So, well, in a sense, as Bram pointed out, the tempered dual is the same as the primitive ideals of the C-star of G. So, in a sense, studying them is equivalent. But yeah, no.
Yeah, but then you come to this. This is a philosophical point, right? So if you have a C-star algebra, you can choose to study the primitive ideals, and that's just something you can do. It doesn't contain all the information about the C-star algebra, and neither. So there seems to be a non-two-way thing here. It also surprised me. So as people in the audience may not know, but I don't work on these representation theoretic questions usually. So I learned something by preparing these lectures. But it seems that this K theory is it's capturing less somehow than.
Definitely. The K theory is this shows. I mean, people like us care about K theory, so we want to compute this K theory. And you see exactly what information it captures and also what it doesn't capture.
Yeah.
And this is why it's okay. So there is a proof of Kohn-Kasparov by Laforgue, where he doesn't use any representation theory, he just computes the K theory. But this also leads to a proof of Kohn-Kasparov, but it gives more information because it computes C-star reduced of G and not just the K theory.
Exactly, yeah.
I'd just like to make a point here. In that paper by Laforgue, he doesn't compute anything at all. He proves the Baum-Kohn conjecture as an isomorphism. He shows that two abelian groups are isomorphic. It doesn't tell you what either of them is, you see. So the point I'm trying to make is if you want to know what either of them is, you have to use all of these representation theoretic parameters as you've just explained to us. Yes, there's no other known way of doing it.
I guess so. I was thinking that what would be cool is to, without using describing the group structure of reduced group C-star algebra, and from that deducing the classification of representations from. But I guess it's there. Perhaps it's naive to think like that because they're kind of the same thing. Perhaps.
Yeah. Yeah, on that level, it's not so surprising that you see that.
I mean, if in the 1950s, if Harish-Chandra's end goal was to describe C-star reduced of G, he would have proved all his theorems with that goal in mind and then written down C-star reduced of G after 25 years of monumental work. But now he did all those theorems with a different goal, and then we just borrowed them and described.
Yeah.
Can I add a comment as well? Can you hear me?
Yes.
Yes.
So there's another hopeful approach to this K-theoretic stuff, which is the work of Nigel Higson and Alexandra Avkoustidis, which is to replace these difficult semi-simple groups by the Cartan motion groups, which are just a semi-direct product of a compact group with an abelian group, for which the representation theory is much, much easier because it can be just done with Mackey's machine. And so they've got results which show that despite the fact that these Cartan motion groups are much, much simpler, the representation theory is extremely similar by some deformation procedure, and that you can hopefully use the understanding of the Mackey machine for these semi-direct products to understand, at least at a topological sort of K-theoretical level, the structure of the representation theory for the semi-simple groups. So it's just a remark to throw another point of view on the problem.
No, that seems something like you use really tools on the C-star algebra level too. Yeah, so that sounds like something genuine on that. So these with the motion groups, they are Morita equivalent, or they're just no?
No, they fit into some.
I don't think
they fit into some deformation family. So there's some way of deforming the semi-simple groups into the Cartan motion group to get a one-parameter family of groups, see, Pierre has some comments. Maybe we should bring him on this as well. This one-parameter family doesn't give a direct equivalence, but it gives you some hope of describing the K-theory of the Cartan motion group in terms of the K-theory of the semi-simple group. Yes, maybe Pierre should jump in here.
Alexandra.
Yes, I can maybe jump in. So the two groups we are mentioning, the reductive group and the Cartan motion group, are different, and the reduced C-star algebras are certainly not Morita equivalent. However, in a certain sense, the C-star algebras admit filtrations, and the subquotients of the filtrations look very much alike in both sense, and they fit together in some field of C-star algebras, which is Morita equivalent with a constant field. So the thing is not completely rigid up to Morita equivalence when you deform one group into the other. But there are filtrations whose subquotients are completely rigid up to Morita equivalence in the deformation. These ideas are completely due to Nigel Higson, and I just filled in the general details, but yes.
And the computation of the reduced algebra of this motion group, then you use the representation theory of that, like, down here, kind of, but it's an easier thing, I think.
Yes, it is much easier. In a sense, you can see that on the topological level, the motion group is just an extension of a compact group by an abelian group. And this makes the description of everything, Fourier transforms and all that much, much simpler. Okay, but perhaps we are getting away from the main track.
Pierre has some comments in the chat box. I guess there was a question about what description of the maximal C-star algebra, not the reduced one. And Pierre is pointing out that it's more or less difficult as describing the full unitary dual and its topology. But apparently there are some results for nilpotent groups for Ludwig and his students. Yeah, I guess Kohn-Kasparov was proven for nilpotent groups by Rosenberg earlier or something like that. I wonder if yeah, I don't know too much about the nilpotent groups, but I guess there's this description of the representations classification is, I guess, easier, maybe more neat.
Yes.
Mm. Right. Any other comments or questions? All right, then I propose we thank again our two speakers, Bram and Peter, for the first half of the summer school. Thank you.
Thank you.
I'll stop the recording now.